first highlight from Unit 3, I'm actually going to skip sequences. There are formulas there. They relate to linear and exponential functions. You can treat them just like linear and exponential functions and use the formulas as they are written. What I am going to go over, though, is the graphical behaviors. Again, we did some of these last class. Remember that linear functions over equal length input value intervals, the output values change at a constant rate. For quadratic, over equal length input value intervals, the average rate of change of the output values change at a constant rate. Last class, a lot of us missed the question on the whiteboards that asked you if it was linear or quadratic by giving me yes that it was quadratic, but with the incorrect reasoning. So I do need you to focus on the reasoning. We also discussed last class that for higher degreed polynomials, that over equal length input value intervals, the nth difference of the outputs is what is constant. So for quadratics, the second difference is, which is why it's degree 2 quadratic. That's the change in the rate of change. But then we get into Unit 2, which is all about exponentials and logarithms. And so we have more graphical behaviors to talk about, or from tabular stuff, from tables. Exponentials over equal length input value intervals. The output values change proportionally. Notice that for each option up to now, the beginning part of this sentence was the same. What does it say in the beginning part of the sentence? Input value intervals, which means the x's are changing like +1, +1, +1, +1. For logarithmic functions, however, notice the words change. The input values appear to change proportionally over equal length output value intervals. This is because exponentials and logarithms are inverses of each other, so we basically reversed this sentence. The input values appear to change proportionally over equal length output value intervals. That's the opposite or the inverse of this sentence. Exponentials and logarithms are inverses. The other thing I want to point out to you, mainly a couple things on this front page. We're going to jump down to where it talks about inverse functions, because you guys have proven to me that we're good at the composite functions, evaluating multiple functions at the same time. Inverse functions, I need you to put a cloud to bring your attention to this little sentence right here. For FRQ1, if you're trying to tell me that a function is invertible, this is the sort of response you're trying to give me, because it asks you to talk about both the input and output values of the function. So each output value of f is mapped from a unique input value. That is why a function would be invertible. Or if it's not invertible, you'd say each output value of f is not mapped from a unique input value, and then you'd give examples. The other thing I want you to notice on inverse functions, a lot of people panic on these, but I'm going to highlight the same word like 8 times. Look at this word I'm highlighting a bunch of times. What am I highlighting? We're switching the x's and y's, switching the inputs and outputs. That's the main concept here for inverse functions. Switching the x's and y's. Last two topics on this front page, which is kind of like the miscellaneous page for this unit, is all about residuals. Residuals are very easy when we're given multiple choice questions for the most part. A lot of times you're going to be asked if a model for data is appropriate, and a model for data is appropriate if it appears without a pattern. So if you see here, this is a pattern of some sort. They all follow a trend, so it's not appropriate. This one in the middle follows a trend. It's not appropriate. You see how this one's like scattered? That's an appropriate model. So the residuals graph will show you an appropriate model. The last topic here is the properties of exponents and logarithms. We've already discussed slightly today because it was on your three-peat. But what I want you to do is add some annotations to MADSPAM. MADSPAM is the acronym that we are using to remember these logarithmic and exponential rules. If you are doing exponentials, you are probably moving this direction on MADSPAM. Because if you are multiplying bases, you add the exponents. If you are dividing bases, you subtract the exponents, top minus bottom. If you are raising a power to a power, you multiply those exponents. However, If you're dealing with logarithms, since logarithms and exponentials are inverses, it's like you're using MADSPAN backwards. This is for logarithms. Because if you have a number multiplied in front of a logarithm, you're going to make it a power. If you are subtracting two separate logarithms, you condense them by division. If you are adding two separate logarithms, like we did on our warm-up today, you multiply their insides. And that's what these rules down here show you with examples, but really you can condense that all down to MADSPAN. Multiply, add, divide, subtract, power to power, multiply for exponentials, or reverse the pattern for logarithms. Okay, like I said, the main topics in this unit is exponential and logarithmic functions. So the next 2 pages focus on those 2 things. Go ahead and flip it over to the next part that says exponential functions. Exponential functions are of the form a times b raised to the x power, where the base b is going to be bigger than 0. A geometric sequence can have a b value or a rate that's positive or negative, so it flips signs, but an exponential function itself will always have a positive b value. The a represents the initial amount, and the b represents the base. I want you to highlight the a value in a particular color, and notice that the a value is in front of the base, aka it does not have the exponent on it. For both of the examples that are shown here, the a value is greater than 0. So see how the y-intercept, or the initial amount, is above 0, above the x-axis? If a is less than 0, all that means is that the graph is going to reflect over the x-axis, or your initial value is going to be negative. So when you're sketching yourself a graph, you would graph it differently. The other thing I want us to notice about this graph is that the range of an exponential function is not all real numbers. The range will always have a lowest or highest, but mostly lowest point, because this function has a horizontal asymptote. Those horizontal asymptotes, for the most part, unless we have transformed this graph and moved it up, appears at the x-axis. That's the lowest this graph is going to go. It's what we approach on one side of our end behaviors, because we have a horizontal asymptote for one end behavior of this graph. So the main idea with exponential functions, and like 90% of the questions that come with it, if you can sketch what the graph looks like, 90 might be a little high. 70% of the questions that come for exponentials, if you can sketch what the graph looks like, you have a better idea of what the question is asking you. If we're on the calculator section, obviously you can graph the function, but we just need to know what the shape generally looks like to answer a lot of questions, because exponential functions are kind of boring when it comes to graphical behaviors. The exponential functions are always either increasing or always decreasing. So growth is increasing, decay is decreasing. Therefore, since they never switch from increasing to decreasing, they will have no relative extrema. There's no relative maximums or minimums. The graph is bounded by a lowest point, a lowest line, your horizontal asymptote, but we have no local extrema, maxes and mins. Exponential functions are also always concave up or concave down, depending on if we flip this over. I guess these are both concave up, but if we flip it over, concave down. Therefore, since they never switch from concave up to concave down, they have no points of inflection, which means there's a lot less graphical behaviors we can talk about when it comes to those vocabularies that we did with polynomials last class. And like I talked about end behavior, since one side is going to increase or decrease without bound, and the other side is going to approach your horizontal asymptote, your end behavior is kind of interesting here. Your end behavior will always have one of them approaching the horizontal asymptote. Whatever that horizontal asymptote is, which may be elevated if you've transformed your graph up or down, but whatever it is, one of your end behaviors is going to be that number of the horizontal asymptote. The other one will either be positive or negative infinity, negative if it's flipped over. Again, a lot of questions when it comes to exponentials. If you can just give me a sketch of what the graph looks like this amount of a sketch, you've got a lot of chances of knowing what the question is asking you. One of the main topics, though, after we discussed the properties of exponential functions, we talked about transformations of them, but not the way you did transformations in Algebra 2. We talked about how we can manipulate these functions to get every horizontal translation to actually be a vertical dilation. And this comes from our exponent rules. Because if you notice, plus h is on the inside. Inside adding is a horizontal translation. But my exponent rules tell me that if I'm adding the exponents, that meant I multiplied the bases. Therefore, I can pull this number out and make it a vertical dilation. Similarly, every horizontal dilation of an exponential function is equivalent to changing the base of the exponential. This is the only way you ever change the base of an exponential, by the way. Like, let's say we have b raised to the 5x. Well, I can separate that into b raised to the 5 raised to the x from my mad spam rules. So now my base, the thing that has an exponent, is no longer b, it's b raised to the c. So you can manipulate these equations based on your mad spam rules to change them in some way. A lot of these questions, you will see what you need to do by reading the answer choices, and it's going to say it became a horizontal dilation. So you're like, your brain's going to go, oh, I need to manipulate this in some way, and you're going to change the function. Major questions about exponential functions. Are we feeling okay? Fast and furious. Let's go to logarithms. Again, the less I talk, the more you guys get to think later on your own. Logarithmic functions are the inverses of exponentials. Notice that the letters that I use when I'm going to put a little cloud around the basic function for a logarithm, they're the same. Obviously, log is there. But a and b are still there. The b is the base and it never changes, just like the base was in the other one. The a here, though, does not represent the initial value. It represents a vertical dilation. Since these are inverses of each other, and inverses meant we are switching things, we've switched the domain and range. This time, the domain is restricted from 0 to 100. 100? What? 0 to infinity? I don't know. Which means that this has a vertical asymptote. There's a boundary on the left or on the right of this function instead of on the top and bottom. So I'm calling these logarithmic, quote, growth and logarithmic, quote, decay functions because they come from the exponential growth and decay. You don't actually use those words to describe logarithms, but here we are. So a logarithmic growth function has a vertical asymptote at the y-axis. A logarithmic, quote, decay function, again, not the same, but it gets us in the right mindset that it's going down, so decaying, right? That's why I'm using that word. It's not official or anything, but it helps me think about it. In this one, the vertical dilation, notice, is negative. So that means we have a negative number in the front. We've already flipped over the function. We flipped this function over the x-axis, but notice the vertical asymptote is still where it was. The vertical asymptote is still at x equal to 0. This comes from the fact that you cannot plug negative numbers into the argument of a logarithm. Not that the numbers inside of it that you plug in can't be negative, but we can't evaluate and make a negative number inside a logarithm. It's not allowed. I'll be honest, I copy-pasted this from the other side and then changed the graphs. This is unnecessary because this and this are already reflections of each other. Politely ignore. Thank you so much. Logarithmic functions are always increasing or always decreasing. Again, kind of boring. They're either always increasing or always decreasing. Since they never switch increasing or decreasing, this means that just like exponentials, they have no local extrema, no maxes and mins. And since they are always either concave up, this one, or concave down, this one, and they never change from that, they have no points of inflection. Kind of boring, but kind of nice. The end behavior for this one is very weird because can we actually reach the full sides of the graph here? No, because we have what as a boundary line? We have a vertical asymptote, yeah. We have this vertical, why is that so long? We have this vertical asymptote here which keeps us from going to negative infinity. So instead of going to negative infinity, look at the left side end behavior. What is the limit going to? 0 on the right side. So the little plus sign means from the right. We're approaching 0 from the right. And that's the little words right here if you wanted to you know what, let's put a little arrow there. That's helpful. We're approaching 0 from the right is how you would talk about that. Because we cannot approach 0 from the left. We can't even hit 0 because it's a vertical asymptote. We for real can't go to negative infinity. So we approach the farthest we can go to the left, which is 0, but we're coming from the right side. So that is the way that you'll write a limit statement there. But notice, this time we're not putting an equal to number as a horizontal asymptote because there is not one. This one will be back to being your positive and negative infinities. So again, being able to sketch what the graph looks like, very helpful for answering questions. You can read that transformations of logarithms. I'm going to go down to semi-log plots. Semi-log plots where the y-axis is logarithmically scaled, exponential functions will appear linear. I need you to highlight that sentence right there. Exponential functions will appear like straight lines on semi-log plots. So if you see a semi-log plot and see that the dots make a straight line, don't think that this is linear. No. It's only appearing linear on this log scale. It's actually an exponential function. And how do we write that exponential function? So glad you asked. And this is definitely a formula that people that were with me for my AP review last week forgot. I even forgot for a hot second how to go look it up. So we'll put a little cloud around this. The exponential function y equals a times b to the x will always move and translate into the following. I'm highlighting so that I have it. Do you see how the a and the b became part of the linear function, but the linear function has logs in it? This is pretty confusing, especially because it reverses the order. So it's log base b, sorry, not base b, log of b times x, that's your slope, log of b, plus log of a, that's your initial value.
So do we use that formula for logs?
If it asks you to linearize, I struggle saying this word, linearize an exponential function on a semi-log plot, yes. A lot of the questions I've seen, though, have asked they give you this equation, the log one, and they're like, what was the exponential function that created this? So you just need to grab the b and the a and put them in the right order. That's many of the questions I've seen here. Otherwise, with semi-log plots, the main thing I've seen is plotting points. Y'all were really good at that. Or telling me this sentence, exponential functions will appear linear. Yes. Yes. Last but not least, solving exponential and logarithmic functions. This is a big chunk. This was what we did on the second question of our FRQ, oh my gosh, of our three-peat this morning. It's so important that you remember the log loop. Because if you have a question where there's only logarithms on one side or exponentials on one side, we can't do the like bases or like logarithms thing that we did on our three-peat. Instead, we follow these steps. If there are multiple bases or log terms, use the properties of exponents and logarithms to simplify them to one term. What are those properties? That's mad spam. Once it's condensed down to one logarithm or one base, you're going to rewrite the equation to its opposite form or inverse form using the log loop. If you started off with an exponential, you create a log. If you started off with a log, you create an exponential. They go back and forth. After that, you solve for the variable as needed, maybe linearly or it's a quadratic. You check for the extraneous solutions if you're solving a logarithm, because you can't plug in negative arguments to a logarithm. You'll round answers to the nearest thousandths. I've been telling you 10 thousandths all year because 4 decimals. The test will tell you 3 decimals, but round to 4. If you can use a calculator or simplify any well-known logarithms or exponential expressions. What are well-known logarithms, exponentials, and expressions? Thank you for asking. That's what your GIM kits are going to be today. It's things that the AP exam expects you to be able to do without a calculator, like 3 to the 3rd power, 27, or log base 3 of 27, 3. It expects you to know these like multiplication facts.